In this video, we're going to study the properties of solids and the phase diagram.
It's time to have a little bit of a serious conversation.
The learning targets are the following. Describe the difference in structure of crystalline and amorphous solids, identify the parts, and interpret phase diagrams.
Bueno.
The essential question is, how do the forces between particles determine how liquids behave, how solids are built, and how matter changes phase? Now, the big idea here in properties of solids is that solids differ by how particles are arranged. Okay? The arrangement of particles in a solid affects the behavior, property, reactivity, and diffusion of solids. The first solid that we're going to study is the crystalline solid. So here, the particles, and when we say particles, we mean ions, atoms, and molecules. They occupy positions in a repeating 3D pattern. So meaning the pattern is highly ordered and long range. Okay, so this is built from a unit cell that tiles. So I want you to think of a Rubik's Cube. So each cube is a unit cell. And when you build a Rubik's Cube, you will have a crystalline structure or a crystalline solid. So here's a unit cell. Here, the points here are called the lattice points. This is where you can see the particles. Okay, when you build many of them, you will form a crystalline solid. Unit cell is the smallest repeating unit of a crystal lattice. Now, this is important because it causes anisotropy. These are properties that depend on the direction of the atoms. For example, here in quartz, depending on where the light enters, the speed of refraction differs. Crystalline solids also have sharp melting points and distinct cleavage planes. Another example of crystalline solid would be table salt. Here are the different types of crystalline solids. We have ionic. Ionic, the units would be the cation and the anion. So if you have a cation and anion, you will have an ion-ion interaction, or basically ionic bonding. Since this is a very strong bond, key properties would be high melting point, they're hard, some are brittle, they're non-conductors as solids, but when they dissolve in water or when they are aqueous, they conduct electricity. For example, salt. Salt is brittle and conducts electricity when dissolved in water. Another type is the molecular solid. Here, the unit would be neutral molecules. Therefore, London dispersion forces, dipole-dipole, and hydrogen bonding are present. So the dominant one would be London dispersion force. Since this is so weak, intermolecular force, the key property would be low melting point, they're soft, they're often volatile, and they are non-conductors. Another type would be the network covalent. The unit would be atoms in a 3D network. The bonds present are covalent bonds. Now, they have very high melting point because of the network, not because of the bond. Remember, ionic bonds are stronger than covalent bonds. But because of the 3D network, they have very high melting point. They're very hard. Most of them are insulators. Usually, they are poor conductors. For example, diamond and quartz. The last type would be the metallic crystalline solid. Metal atoms, or cations in the lattice point, and the localized electrons, meaning the electrons are moving. Because of that, this will have metallic bonds. Key properties include excellent conductivity, they're malleable or ductile, they're lustrous, meaning they're shiny, and the melting point would depend. Often, the melting point is high. For example, copper, iron, aluminum. The next type of solid would be amorphous solids. Structure, you have to remember that there's no long-range order and no crystal lattice. They only have short-range or local ordering. So they are often described as frozen liquid network. Now, amorphous solids, they have a range instead of a single melting point. Generally, amorphous solids are isotropic, meaning same properties all throughout. Amorphous solids will also exhibit viscoelastic flow over time, meaning the flow or the movement is viscous and at the same time elastic. Here's an example. If you notice, they're both silicon dioxide, but this one on the left is a quartz. This one is a glass. The structure of quartz, crystalline solid, is repeating and ordered, whereas in amorphous, it's chaotic. Here's the summary of the features of crystalline solids and amorphous solids. Now that we're done with the properties of liquids and solids, we can now study how they change. And to know that, we need to study the phase diagram. From the name itself, it's a graph or a picture that represents the changes in phases of a molecule. In simple words, phase diagram shows you stable phases as a function of pressure and temperature. Now let's study the parts of a phase diagram. The first one would be the regions. These are areas where one phase is stable. You have solid, liquid, and gas. Now at any point inside the region is that phase. Any point inside the region is that phase. For example, look at this cursor. If this cursor is here, this cursor is the gas. But if I move here, that is a liquid. Here, that is a solid. Notice that I moved along the curve. This is another feature of a phase diagram. We call them boundaries. Boundaries are equilibrium lines where two phases coexist. Crossing a line or passing through a line, meaning there is a phase change. So what I did here from gas, look at this cursor. When I cross this curve, I become liquid. And that is what we call condensation. Condensation is gas to liquid. But if I start here from liquid, going to gas, that is vaporization. So this curve, this line, is called a vaporization curve. We also have the fusion curve, which is melting or freezing, depending on where I started. If I start here from liquid, it will become solid when I pass through the curve. That is freezing. If I start from solid, it becomes liquid, that is melting. And I also have the sublimation curve. If I have here gas and it becomes solid, that is deposition. If I have a solid turning into gas, the process is called sublimation. There is a change of phase. Now there are two important slopes that you have to know, and it has to do something with the fusion curve. Now the tilt of the fusion curve tells you how melting point changes when pressure increases. If the line slants up as you move right, it means that more pressure, higher melting point. So therefore, the solid is more tightly packed than the liquid. Now, if the line slants down, negative slope, more pressure equals lower melting point. Therefore, the liquid is more tightly packed than the solid. So this graph on the left shows a positive fusion curve. So most substances follow this curve. This is because solids are denser than their liquids. So if you increase the pressure, it will favor the solid, meaning you will need higher temperature to melt them. Therefore, melting point goes up with pressure. However, if you have water, it's usually a negative slope. I want you to remember that ice is less dense than liquid water. Therefore, increasing the pressure favors the liquid. That's why you need less heat to melt water. So the melting point goes down with pressure. Another point that you have to know is the triple point. The triple point is where all phases are in equilibrium, meaning the compound changes phases at one exact temperature and pressure. I want you to look at this example. This water. Another point that you have to know is the critical point. This is the end of the vaporization curve. Beyond this point, liquid and gas can no longer be distinguished. Therefore, we call them supercritical fluid. Supercritical fluids have gas-like diffusion and liquid-like density.
I hope this somewhat made sense.